All right, now we're going to start a whole new section. Originally, okay, we started off in chapter 1 that dealt with linear equations, straight lines. Linear equations. Like y equals mx plus b. Those were straight lines. Kind of straight there. Then we moved to quadratic equations. And those had this form, ax squared plus bx plus c. And they look something like this. Now we're going to move on to something called polynomial equations. Polynomial equations or polynomial functions look like this. Oops, I have these backwards. It should be a sub n x to the power n. A sub n minus 1 x n minus 1 dot 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 ax a. That's a polynomial function. Polynomial simply means, poly means many, nomials means numbers. Many numbers. A linear equation could have one term, like linear equation, like be horizontal line like 3, or it could have two terms. Quadratic functions have three terms. They're called trinomials. So this is called either a monomial or binomial. Quadratics are trinomials. Because they have tri means 3, bi means 2, mono means 1, poly means many. So what we're going to be doing now is we now have pretty much no limit to how many terms we can have in a function. That's what this chapter is about. So I can give you any size. We can have to the degree. Remember, that's the highest exponent. Highest exponent. It used to be 1, then it became 2, and then now it's anything higher than 2. The height, it tells us the maximum number of solutions. Remember, solutions are x-intercepts. We also call them zeros. And we'll also look later at, we call those factors. But these are all synonymous. If I say solutions, I mean x-intercepts. So if I mean x-intercepts, I mean zeros. It's just the only thing different between them is how they're written. The term involving the largest exponent, the very first term, is called the leading term. It consists of a sub n, which is called the leading coefficient, and then the x sub n, which the n gives us our degree. And together, those two will give us an indication of what the entire graph is supposed to look like. Right, so let's start looking at these things.
So even though we're using n as a placeholder for both of these, n isn't necessarily the same number, correct?
For the first one, yes, correct. Yes, because let's say we had x to the, let's say we had this polynomial. Hey, we have this polynomial. The degree is 5, which means 1, 2, 3, 4, 5. The degree is 5, but notice we have 6 terms. Same with the quadratic equation. Quadratic was 2, and we have 3 terms. The linear equation, the degree 1, but we have 2 terms. So there's always one more term than the degree because we have to factor in the constant. And all the a does is this tells us that this one is a sub 0. This is a sub 1, a sub 2, a sub 3, a sub 4, and that's a sub 5. So it just allocates which one it's associated to. But this one here is, it just tells how many terms, which term our coefficient belongs to. And degree is 5. So it
That makes
doesn't
sense.
this
Thank you.
it makes okay, yeah. I mean, but that's now if we're missing a term, that a sub changes because we're missing a term, but the n will still make it a 5th degree polynomial. So yeah, that was a great question. Is that will always be no? We may have equations that could look like this. It's got 3 terms. Is it a 7th order polynomial? Yes. Or a 7th degree polynomial? Yes. Even though it only has 3 terms, which is what quadratics have. So this is a sub 0, this is a sub 1, and this is a sub 3 because we only have 3 terms. Now, when we get ready to graph these polynomials, we're going to have to notice certain pieces of the function. To graph polynomials, of degree n. We're going to have to find a couple of things. We're going to, the leading coefficient is a. A to the n. That's what we'll call those. We're going to have to figure out what the zeros are, or the x-intercepts. Remember how we find those? We find those by setting the function equal to 0 and solving for x. We're going to have to find the y-intercept. That's the point 0, y. the maximums, the minimums. Now we'll look at that in a second. We're going to have to understand what the domain is. And our range. These are the pieces, once we have those, we start putting the functions together. Now, maximum minimums are what we call the vertices. We're only looking for the local extrema. Because the high and low, the highest and lowest really isn't important. But what we're looking for is once we find the vertices of the function, then it'll help us graph it. For example, let's look at these three graphs that we have so far. Linear only has one x-intercept. Quadratic equation can have two, or two, you can have one or zero. But, so this is x squared, this is x. What if we had x to the fifth? It can look something like this, where the ends keep on going further and further and further. These are the local maxima and local minima. But these are the maximums, and these are the minimums. And we're going to be able to, once we find the x-intercepts, these guys, we'll be able to tell what's happening at both ends of it, and then whether we're going to have a maximum or minimum at between each of those points. All right, so polynomial versus non-polynomial functions. So polynomial functions are all the functions in our library of functions. So we have those, the linear, we have the constant function, we have the quadratic function, we have the cubic function, and so on and so forth. Non-polynomial functions, these are the ones that have points, that have restricted domains, difference between this one and this one. This is a corner. This is a point. It just comes into a point. Or our example of 1 over x, where it's not continuous. So the function has to be continuous. And it can't have sharp edges or sharp points. But like I said, earlier, I said that we can tell what the graph's going to look like. Any polynomial function I have and it goes all the way down to a sub 1, x sub 1, a sub 0. The leading term dictates everything when it comes to the graph. Now, if the degree is even versus odd, that's going to give us something unique about our function. So is the degree even versus odd? There's odd. If the degree is even, and now from a library of functions, we have x squared, x to the fourth will look something like this. Which it has to have at most 4 x-intercepts. And so on and so forth. X to the sixth will look like this. But these waves in the middle don't have to be there. I mean, they don't have to be that uniform. One can go up really high or low, very low. So now the other side is odd. We have a linear function. The cubic function, this is x cubed. And this is x to the fifth. That's what they'll look like. So what we notice is if n, this is the degree, is even, the ends of the graph point the same direction. So when x squared, x to the fourth, both ends point the same direction. They can either point up or they can point down. This is what we're going to talk. This is what's called end behavior. This is what happens to both ends of the graph. We're just looking at the function, and we can tell what the ends of the graph are going to be doing, or going to look like by looking at the degree and something else. So if our degree is odd, the ends of the graph point int in opposite directions. Notice in the linear equation, up and down, cubic, up and down, and the fifth order, and so on. So that's just by looking at the degree. Another thing, the end behavior deals with the leading coefficient. The a sub n. If a sub n is positive, the graph is increasing, which means as the x gets bigger, the y gets bigger. If the leading coefficient is negative, the graph is decreasing. Which means that as x goes to positive infinity, y goes down to negative infinity. So as x goes to infinity, y goes up to infinity. As x goes to positive infinity, y goes down to negative infinity. So this is made more simple by what's called the leading term test. This is called the leading term test because all we look at is for any polynomial, we look at the leading term. And here's how we determine the end behavior. If A, the leading coefficient, is positive versus the leading coefficient is negative, n is odd versus n is even. This is only for end behavior. So all we're looking at is, now what these points represent are the farthest left and farthest right y-intercepts. Farthest left and right x-intercepts. So if n is odd, that means they point in different directions. If A is positive, that means it's increasing. So they have to point opposite directions. So that's what's going to happen there. We don't know what happens in the middle, but we know at the end, that's what the graph's going to look like. If A is negative and n is odd, then it's a decreasing function. So they have to point opposite directions. If n is even and A is positive, they both point the same direction, and it's a positive, so it's going up. If it's negative, they go down. Right, so that's just by looking at the function, we can see what's going to happen. Example 1. It's actually matching, but I'm just going to show you these. And we're going to guess what the graph looks like. Negative 5x cubed minus x squared plus 4x plus 2. And number 3, C, f of x equals x to the 5th plus 1/4 x plus 1. And the last one, f of x equals negative x to the 6th plus x cubed minus 4x. No, that's to the 5th. I'm sorry, middle's to the 5th, and that's x cubed. So we're going to look at these and we're going to try to guess what it looks like, and then we're going to compare them to the 4 choices we have in our multiple choice. All right, so what do we have here? A is 3, N is 4. So A is 3, N is 4. So it's positive and even. Since it's even, both ends point in the same direction. So, since A is positive, they both point up. Whatever graph has this shape, since it has 4, you can have at most 4 x-intercepts. Here, the next one. A is negative 5, N is 3. So we know at the ends, because it's an odd degree, they point in different directions. Since A is negative 5, that means the right side goes down and the left side goes up. And since the degree is 3, it can look something like this. It crosses 3 times.
So what we're being able to learn here from looking at these equations right off the bat is we know the general shape of the graph, but we still have to solve for the x-intercepts, yeah?
X-intercepts and the points in between, right? That's the long part, and which is what section 4, 3, 4 of this chapter deal with. And it's a lengthy process, but it's the only way we can solve these. Yeah, so this is the easy part. We're getting that part done first. Okay, A is the leading coefficient. It's 1. N is 5. So this is odd, and this is positive. So at both ends, we know they point opposite directions because it's odd, and it increasing since A is positive. It looks something like this. And the last one, A is negative 1, N is 6. So all we know for sure is at the end, since it's a even degree, they both point the same direction and they both point down. So looking at our options in our sheets, let's look at the first one. Both ends point up. So out of these 4 graphs, which one has both ends point up? It's D. So A has to be capital D. Because both ends point up. Number two, it's got to be going up to the left, down to the right. So up to the left, down to the right. Only one that matches that is B. Number three, down left, up right. Down left, up right. It's got to be A. And the last one, they're both point the same direction. They both point down. And the only one that does that is C. Notice how C, it's a 6-degree equation, but only has 2 x-intercepts. And that's another thing we're going to talk about. What happens if a graph has high degree, but only has a couple of x-intercepts? And that's what we'll look at shortly. And this next part, we're going to do the simple stuff first, and then we're going to start building up to that as the chapter goes along. As you said, we know what the end of the graph looks like, but we have to figure out what the x-intercepts are. So that's what this part is. Finding zeros of polynomial functions. Zeros, solutions, intercepts, they're all the same thing. So the example they're giving us in this first one is pretty straightforward. And to find zeros, because it's a polynomial, it has to set equal 0 on one side, and everything else has to go to the other side. Because in this case, it's quadratic. We can use the quadratic formula. We can use the complete the square. We can try to use factoring. So let's just try the simple one first. It just, we cannot use complete the square or quadratic formula on anything higher than degree 2. It only works for quadratic equations. So I can tell you that the only method we can work for higher order polynomial functions is factoring. That's the only thing that'll work. So in this one, we know that both of these are x's because we're solving for the middle term. X and x. The second sign is a minus, so they're opposite signs. One's positive, one's negative. And since it's a minus, you look at the first sign, and that the bigger number gets that sign. So now we got to figure out what times what is 8. When we subtract them, we get 2. What times what equals 8? In this case, since the second sign's a minus, when we subtract them, we get the middle term, 2.
4 and 2.
4 times 2, 4 minus 2. And the bigger number, since the first sign is a negative, the bigger number gets the negative. All right, we factored it. Now we take both of these terms and set them equal to 0. That's the zero product principle. If you have two numbers that multiply to equal 0, that means the first one can be 0, or the second one can be 0, or they can both be 0. And we're taking they both be 0. Solve for x, and there we have our x-intercepts. So we know in our graph that -2 and 4 are our x-intercepts. Okay, now what does that have to do with anything? Well, because it's a quadratic equation, we know that there has to be a vertex that has a axis of symmetry, and it's always the midpoint between the intercepts. So find the number that's halfway between -2 and 4. So we have -1, 3, 0, 2, 1. So 1 is our axis of symmetry. Since A is 1 and it's even, we know the graph will look like this. So it has to go down all the way. The y-intercept is at -8. So we have a y-intercept at 8. And then there has to be another one at 2, -8. Because the axis of symmetry is at +1. So here now we can use, to find the vertex, we can use that -b over 2a and plug that in there. But again, that only works with quadratic equations. In other words, the axis of symmetry, the vertex, will only be in the center point, the midpoint between our x-intercepts on a quadratic equation. It won't always be the case when it comes to cubic or quadratic or anything else higher than that. So we have to work it out by hand. Let's look at cubic polynomials. This one is when you have an x to the power 3. So here's a polynomial function, x cubed plus 2x squared minus 5x minus 6. So far, the only discussion we've had on cubic equations is we use something called the grouping method. We did that a few sections ago, where we put parentheses in the first and second, see if anything factors out, but it won't work in this case. So in this example, I'll give you the factors, because these factors are what's going to happen in later on in this chapter. So this one would factor out to become x plus 3, x plus 1, x minus 2. Okay, another side note here, because the last term is a negative, and there are positives and negatives inside the function, we know there has to be an odd number of negatives. Because if we had an even number of negatives, then it'd be positive times negative, which would give us a negative number. Negative times negative will give us a positive number. We want to look at the last numbers here, because these numbers, if we multiply those, that's where we get the last term. 3 times 1 is 3, times -2 is -6. So it's either if all three of them are negative, or if they're positive, positive, negative. That's just a side note. All right, let's look at example 2. Example. Consider the polynomial p of x equals x cubed plus x squared minus 17x plus 15. It basically says determine if 2 and -5 are zeros of p of x. What it's saying here is determine whether each of the numbers 2 and -5 is a zero p of x. What that's saying is if I plug in 2 inside the first polynomial, inside the function, will it equal 0? If so, then yes. 2 is a 0. So let's check it out. So at p of 2, we get 2 cubed plus 2 squared minus 17 times 2 plus 15. Whatever's inside here goes in place of x. 2 cubed is 2 times 2 times 2, which is 8. 2 squared is 2 times 2 is 4. Negative times positive is negative. 17 times 2 is 34 plus 15. Now combine like terms. We have 8 plus 4 is 12. Minus 34 plus 15. Let's do the pluses. 12 plus 15 is 27. 27 minus 34 is -7. So no. 2 is not a 0 of our polynomial p of x. How about the next one? So this one's not. I put -5. P of -5. X negative. So we have -5 cubed plus -5 squared minus 17 times -5 plus 15. You notice I put the parentheses around if it's negative, put parentheses around them, the numbers that you're putting in. Because if I didn't put the parentheses around it, this number would be -125. -5 squared, it would be -25. Order of operations says do exponents first. And then the negative sits out there. But if I do it this way, I have -5 times -5 times -5. So I have 3 negatives, which makes it a negative. 5 times 5 is 25, times 5 is 125. plus negative squared. Negative times negative is a positive. 5 times 5. So this goes to both of those. 5 times 5 is 25. Negative times negative is a positive. 17 times 5. So 7 times 5 is 35. 5 times 1 is 5, plus 3 is 8. So it's 85. Plus 15. So we could do both of these at the same time. Negative 125 plus 25 is negative 100. 85 plus 15 is 100. Negative plus positive 100s is 0. So negative 5 is a 0 of our polynomial. Right, so those are our zeros. That is our zero, I should say. Let's look at another example. Example 3. Example 3. Find the zeros of this polynomial. F of x equals 5, x minus 2, x minus 2, x plus 1, x plus 1. Okay. Remember, it helps us if we know what a and n are. N tells us the number of solutions. Well, we have 1, 2, 3, 4 solutions. So n equals 4. Because we have x times x times x times x. So there's x to the 4th. A is the leading coefficient times the coefficients of all these inside the parentheses. So 1 times 1 times 1 times 1 times 5 is positive 5. So we know what the graph's supposed to look like. It's even, so both ends point in the same direction. It's positive, so they're both going up. But let's look at this. Our solutions are x minus 2 equals 0, x minus 2 equals 0, x plus 1 equals 0, x plus 1 equals 0. So our solutions are x equals 2, x equals 2, x equals negative 1, and x equals negative. So our solutions are really x equals positive 2 and x equals negative 1. We only have 2 x-intercepts, even though they're repeated a couple times. And it's a 4th order equation. So we know in our graph, at negative 1, we have an intercept. At 2, we have an intercept. Our y-intercept, the y-intercept will be at the leading coefficient. So take 5 times negative 2 times negative 2 times positive 1. Remember, to find the y-intercept, set your x equals 0. So all these x's disappear. Negative 2 times negative 2 is 4. 4 times 1 times 1 times 5. 4 times 5 is 20. Because remember, it has to be going up because it's a fourth order equation and both go up and a is positive. So it has to go all the way down here to negative 20. Now, if we look at this equation, we'll notice something. You'll notice we only have two solutions. But that equation can be written like this. Oops. So we have our f of x was 5x minus 2, x minus 2, x plus 1, x plus 1. What we could do, since both of these are the same and they're multiplied together, we'll say x minus 2 squared. And this other one occurs twice. Now, look at these. These have a name. The exponents, or the exponents of our factors. These are called multiplicities. The sum of these exponents equals n, your degree. So 2 plus 2, n equals 4. Actually, this graph is not the right graph. The graph of this one, which we're going to talk about now, let's look at the graph of this one. The earlier one is not correct. So we know we have, for this one, our y-intercept was 20. Our x-intercepts are at 2 and negative 1. N was 4. A was 5. So this graph is going to look something like this. How do I know that? Well, if we look at our equation, we had 5x minus 2 squared, x plus 1 squared. If the multiplicity is even, the graph bounces at that intercept, or that 0. So since there's both positive, it bounces. If the multiplicity is odd, the graph crosses at that 0. So this graph I put here was not to this one because I miswrote that question. If I had x minus 2, x minus 2, x minus 2, x plus 1. So we have 3 of those, so it's x minus 2 to the third. Then we have the x plus 1. Okay, that's fine. The n equals 4. Well, we know it equals 4 because we have 1, 2, 3, 4 solutions. But notice how we have 3, and there's nothing written there. There's an invisible 1. So 3 plus 1 equals 4. A is found the same way. Look at all the coefficients. 5 times 1 times 1 times 1 times 1 is 5. Our y-intercept for this one remember, set all your x's equal to 0. So it's -2, -2, -2, +1. Negative times negative is positive, times 2 is negative. 2 times 2 is 4, times 2 is 8. 8 times 5 is 40. So the y-intercept was at -40. So at -40, we have a y-intercept. The x-intercepts are at +2 and at -1. They're both odd. Okay, the n is 4, so we know that both ends, they point up. And at the intercepts, since they're both odd, the graph crosses. So it's got a cross between there. So it looks something like that. Right, so that's what the multiplicity is about, and that's what's going to help us draw graphs, or if we have to choose a graph. So we know what the graph answer is supposed to look like. Example 5. Find the zeros. F of x equals x cubed minus 2x squared minus 9x plus 18. So the only method we know how to solve these is by factoring. I mean the grouping method. I take the first 2 terms, put them in the first parenthesis, and the second 2 terms, if it's got a negative, it's got to be inside there also. Now factor both of these terms individually. Remember, we're supposed to have 3 solutions. N equals 3, so we're supposed to have 3 answers. They both have 2 x's in common. So if I take out 2 x's there, I have 1 left. If I take out 2 x's, I have the 2. Now, in both of these, they both have a -9, but that negative has to come out. So you have to factor out the negative, and they're both factors of 9. So if I divide both of these by -9, what happens? Negative, negative cancel, the 9's cancel, so you just have x. Positive divided by negative is negative. 18 divided by 9 is 2. This is a good sign. That's what we're trying to get to. If inside the parentheses, they're both the same. Remember, we only have 2 terms left. Do they have anything in common? Yes, they both have the x minus 2. So if we factor out the x minus 2's, all we have left are the coefficients, and they go in their own parentheses. So x minus 2, well, this one, x squared, 9 is made up of 3, so it's 3 squared. This is the difference of 2 squared terms. The difference of 2 squares is you take the terms x and 3, and give them opposite signs. So our zeros, x equals 2, x equals -3, and x equals 3. Those are our zeros, our x-intercepts. Okay, we know the y-intercept is the constant, is 18, so it's going to be at 18. There's a point there. The intercepts are at 2, 3, and -3. N is odd, and the leading coefficient is a +1. So because n is odd, a is positive, that means the graph at both ends points different directions. Now, does it cross or bounce? Well, since this is going down and it has to cross that one, we know it has to at least do this. Now, does it cross or bounce at 2? Well, we know it's going to do this. How do we know that? Because our multiplicities are all odd. If they're odd, they cross through the x-intercepts. So that's the graph looks like that one. And the last one for this section. Find the zeros of this one. X to the 4th plus 4x squared minus 45. We're lucky because this one is factorable. How do we know it's factorable? Because it's quadratic in form. Take the middle exponent. If we multiply it by 2, we get the first. So it's quadratic. So we have x squared here, x squared here. Remember, we always solve for that middle letter. The second sign is negative, so they're opposite signs. And since the first sign is positive, the bigger number goes there. So what times what equals 45? That when we subtract them, we get 4. And this is the hardest part, but with practice, we get 9 times 5 is 45. 9 minus 5 is 4. So 9 and 5 are our numbers. The bigger one gets the plus, so 9 goes there, and 5 goes there. Solving both of these, we see they're quadratic, so they each have 2 answers. X squared plus 9 equals 0. X squared minus 5 equals 0. We're supposed to have 4 answers. The y-intercept is at negative 45. And our x-intercepts, move the 9 over. X squared equals negative 9. Square root, so we have x equals plus or minus 3i. This is a negative inside a square root, so it's an I. Square root of minus 3. And then x squared equals 5. Square root both sides. X equals plus or minus square root of 5. So these are our 4 solutions. X equals positive 3i, negative 3i, positive radical 5, negative radical 5. I and 3i are imaginary terms, so they don't cross the x-axis. Radical 5, square root of 4 is 2, square root of 9 is 3, so it's pretty close to 2. A little bit bigger than 2. So let's say it's that one. And negative is just a little bit bigger than negative 2. Since n is 4, a is 1, so it's an even degree, positive coefficient, so they both point the same direction. They both point up. No more x-intercepts. So what this graph's going to look like is something like this. Because since the y-intercept is right in the middle of them all, then it has to be going back up for it. All right. How does that sound?
Okay, so essentially, if we're using n, if we're saying, oh, there's 4 solutions, that can kind of be a trap because imaginary numbers can't be graphed. So we have to
Cannot
make
be
sure
good.
we're solving
Yes.
it.
Well,
Okay.
see, and when it does play us 1 point because this tells us we have 2 more, I call them 2 more vertices in our graph, here and here. Even though it's not graphable, it's not an intercept. It will tell us that we will have vertices at those points. But that's why the hardest part, the easiest part, is finding the y-intercept. Then we'll find out the x-intercept. The rest is plug and play because you have to plug in some numbers. So yeah, that's the only part that really bites, is plugging all those different numbers. All right, let's go ahead and do number 2 while we're at it, because number 2 is asking us to, let's start graphing these functions. What do we look for?